Hi, my name is Christian Gagne. I'm the director of the Institute Intelligence et Données and professor at Universite Laval. I am presenting a joint work with Mahdieh Abbasi, a PhD student at Universite Laval, and Arezoo, Rajabi, and Rakesh Bobba from Oregon State University. Our work is on the design of models, that is, ensemble of specialized deep neural networks that are deemed robust toward adversarial instances. So our work aims at making methods that are robust to adversarial attacks. We mean by adversarial attacks, that is modification, really small modifications to the input samples that are not perceptible by human. For example, with images, we cannot see the difference between the original clean sample and the modified samples. But the machine learning model that is trained on a given dataset is fooled by these modified samples. And the point here is to make use of an ensemble of specialists that are trained on diverse subset of classes and that are able to correctly classify the instances when we are facing clean samples, and are able to identify modified samples, adversarial samples, through rejection of these samples. So the point when we are dealing with adversarial example is to deal with samples that are modified with something that is really small, not perceptible, but that can lead the network to be confidently fooled toward classifying a sample in the wrong class. For example, here we have panda sample, which can be correctly classified with more than 90% probability when it is not modified. But with a small modification, we see here some kind of noise I did with a small epsilon, which can be really low, such that the modification is not visible. The network can be fooled to classify with high confidence this image as a given. We know different types of attacks. One of the well-known one is the fast gradient sign, which consists in making one step of gradient ascent, so gradient descent toward increasing the loss. So with just one step, we are able often to generate a modification to the original sample that will be misclassified by the model. We also have a variation that is targeted FGS, where the gradient descent step is made toward modifying one sample into another specific class. So we have a target class, and we try to modify the current sample into being classified as the other class. These two approaches are really fast. They are just one step of gradient descent on the image, but they lead often to non-optimal adversaries. The modification is relatively light, but still is not optimal. We have other approaches like deep fool, where the modification is more important but lead to better adversaries, as it makes a more complex modification to the image by making a projection of the sample in the nearest decision boundary. And we also have Carlini and Wagner, which is a much more sophisticated approach which requires some optimization techniques. So it is much lower but lead to optimal adversaries, really samples that are just smallly modified while fooling the network. And we are also distinguishing three types of attacks. We have black box attacks, where the attacker doesn't have any access to the victim classifier. So basically, the attack is based on a local model, a proxy model that is full toward classifying a sample in another class, and we expect that this modified sample will also be fooling other models. On the other hand, we have white box attacks, where the attacker has access to the full model, has access to the trained model with all the parameters, and then try really to design an attack that is specific to this model, where the model will be full also, but with really maybe a smaller modification compared to black box attacks, and a modification that we know works well with this model. In between, we have the gray box attacks, where we don't have access to the precise model we are using, but we know the configuration used as classification model, so we have access to the specific design without access to the trained model. So we could train another model that is really similar but not the same. And so our goal is to, without using any kind of specific adversarial samples, we want to detect adversarial instances by calibrating our model predictive confidence. And so if we are facing an adversarial sample, we want the confidence to be low, to be able to reject that sample as being suspicious, as being a possible attack. while keeping the confidence on clean sample high. So we are looking to achieve this by having a diverse set of specialists. Also, we are making use of Ensemble learning to learn different models that are dealing with different subset of classes. And so this ensemble of specialists is made of many neural networks that are trained on different subset of classes, plus one generalist network that is trained on all the classes from the dataset. For example, here we have a three-class classification problem. On the left, we have the generalist neural network, which is dealing with the three classes. So we have the points and we have also the decision regions. We could also think about two other specialists. One specialist that is dealing with the red versus green samples. So we can see here that there is two decision regions, green and red. We don't have decision regions for the blue one because it is not a class that is used for training the model. Likewise, we have on the right a model that is trained on red versus blue without having green samples. So here again, we are dealing with two different classes. So we can build an ensemble of three models that way that will deal relatively well with adversarial examples. A black box attack will try to can fool the generalist classifier, as we can see here. If you're taking the sample, the red sample close to the border here, we can see that a small step can transform the samples into a new point in the green region. And so that means that we are able to fool it relatively well. Compared to the two other specialists, we can see that in the middle one, we have a red versus green. That specialist can also be fooled similarly to the generalist. But the specialist on the right is trained on the red versus blue. And so from the same point, it is much more complex to fool the network. The network will not be fooled the same way because it doesn't have the green class, and so the steps required to fool a network is much bigger. And so with white box adversaries, the point is that the attack method will try to modify the sample, but now the modifications between one specialist to another will not be the same. For example, here we see on the left a modification to the generalist will lead us to modify the red point into and move it to the blue zone by gradient ascent in that direction. So this is something that can be done. On the middle figure, we have the red versus green specialist. And using the same starting point, the modification will be different, will be in another direction, because we will try to modify this point into a green sample for fooling the network. And on the right side, we have the second specialist, which will be fooled similarly to the generalist. So we can see here that the modifications to apply will not be the same for all the models. So our approach aims at creating an ensemble of specialists, so that this ensemble will be created in some way. Then we are defining a specific voting mechanism that will merge the member predictions to compute the ensemble decision. And from that voting mechanism, we are able to evaluate a joint prediction confidence that will be used to reject or not the samples based on the value. So if the predictive confidence of the ensemble is lower than a given threshold, we will reject the sample because it is likely to be from an adversarial generation approach, while if it is over the threshold, we can trust it and assume it is a clean sample, and as such classify it in the class we determine from the voting mechanism. So as for making the ensemble, we are first building a fooling matrix by a fast gradient step. So we will look at the link, or maybe the relation between the true classes versus the fooling classes that can be obtained by applying FGS on them. So we can see that from some class we are not transforming a sample into all uniformly into the other classes. There are some classes that seems to be easier as target for the attack. So from that matrix, we will define a subset of classes that are the most likely falling classes for a given class. So we are doing this for all the true classes. For example, here we have the airplane class, and we see that a sample from the airplane class can be transformed by an attack into a sample from the class auto or cat or dog or horse. So that will consist the subset of classes that are the most likely falling classes. And we take the remaining classes as another subset, which is less likely to be the target from an attack with the airplane with an airplane sample. And as such, we are obtaining for each class two subsets, one of the most likely falling classes and another with the remaining classes. So that leads us to 2K subsets, and from each of these subsets we are training a classifier. So we have 2K specialists here, and we also add to that one generalist, which is a model trained on all the classes. We are applying then a voting mechanism. The principle here is that we for each class we have K plus 1 models that can vote for that class. The other K ones are not including that class in their subset when we train them. So we can see that a sample should be classified by all the relevant models to its given class when it is properly classified. So we assume that the K plus 1 models for a given class will correctly classify the sample toward that class. And as such, when we have an agreement when this is happening, that all the relevant models are voting for the given class. And in that case, we are taking we are averaging the prediction confidence over all the models assigned to that class. Otherwise, we have we are facing a disagreement, and in such circumstance, we are averaging the prediction confidence over all the models. So this will lead to a much lower confidence. And we also showed in our paper that with such mechanism, in the presence of disagreement, the ensemble predictive confidence is upper bounded. So assuming that M is the ensemble size, we can see that the confidence will never be over 0.5 plus 1 over 2M. And assuming that 2M is relatively high with in multi-class classification, like when we have 10 classes, for example, this will be relatively small. And as such, we can use as a global threshold a value of 0.5 for rejecting samples as adversaries, potential adversaries. We are making we are making experiments, and these experiments are based on two metrics. So the first metric is the risk rate for clean samples. So this is the ratio of correctly classified but rejected samples. So we count the number of samples that are correctly classified but have a confidence lower than the threshold, and this divided by the number of misclassified but not rejected samples. So this gives us a risk rate for clean samples versus the risk rate for adversaries, which is the percentage of misclassified adversaries that are not rejected. The experiments we made, we first have a set of black box attacks on the MNIST dataset. So we can see here a comparison between our approach, which is the green line with diamonds, the specialist ensemble, and we are comparing our approach with pure ensemble, which consists simply to train an ensemble of many models which are dealing with all the classes. The difference is that these models are trained with different random seed, so we are having as final result different models but trained the same way. And this pure ensemble approach is still more robust than what we call a naive CNN, where we only have one model trained. So for black box attacks, we can see that for a threshold between 0.5 and 0.9, the risk for clean samples is slightly higher than the one we obtain with pure ensemble and naive CNN. So there is a slight degradation, but not that much. It is still really low in terms of percentage. While on the right side, when we are dealing with adversaries, then the specialist, the ensemble of specialists is much better to deal with these cases with a capacity to reject much more samples that are in fact adversaries generated by FGS compared to pure ensemble and naive CNN. And this for threshold up to 0.9. After 0.9, it seems that it is not a good range of value to use for the threshold. Looking now at the same kind of attacks but with CIFAR-10 dataset, the results for clean samples are slightly degraded for the specialist ensemble. So we see that there are more rejection of clean samples, so it tends to reject more, but with threshold over 0.5. So at 0.5 still there is some, I would say, rejection, but the performance is kind of interesting still. Especially for detecting adversaries. On the right side, we see that specialist ensemble is really good to intercept adversaries compared to pure ensemble and naive CNN. So the approach here is able to detect the adversaries quite well. And now if we are looking at white box attacks, we can see that the generation of adversaries that are specifically made for our model, our ensemble of specialists, it's much harder to fool by this approach. So we have a lower success rate, which means that it is much more difficult for the adversary generation approach to fool our model. This is kind of consistent over all the different, over the two datasets tested and the different adversaries approaches used. And now looking at Graybox attack, we can see that if we are generating 10 CW adversarial examples using another ensemble of specialists, so it is the same configuration but a different ensemble trained with a different random seed, and then we apply these attacks on a different ensemble of specialists, about 75% of these adversaries are intercepted by our approach. So that's quite good, because the 25% of the adversaries that are not intercepted are hard to recognize. We can see some example here. So it means that the modification required to fool the network is much bigger, and it can be seen even by human eyes. So it means that it is much harder to deal with our model to fool it. So our contribution is to build an ensemble of diverse specialists. We have an approach that is relatively efficient, so it is relatively simple, and the voting mechanism is also good for calibrating the output, having a really clear differentiation between when we have disagreement, the confidence is quite low, and this often come from adversaries that are presented to the network versus clean samples that are in general well classified with high confidence. And so when we demonstrated that this confidence value, we can deal with it with a global threshold. So thank you for your attention. We are inviting you to contact us if you have any question. We have the contact information here, and we hope you will enjoy reading our paper. Thank you.